and welcome to the second installment of the CUAHSI Cyberseminar series. I'm Reed Maxwell, I'm your host here at Colorado School of Mines, and it's a pleasure again to introduce our second speaker in the series, who is also broadcasting from Europe in the evening. Some after hours, Stefan to come after hours to give this talk. And this week it's Stefan Kollett. And Stefan holds two positions. He's a professor at the University of Bonn in Germany, and he is also a research scientist at the Research Center or Forschungszentrum in Jülich, Germany. Stefan holds a PhD in geosciences from the University of Nebraska-Lincoln, and before taking his joint appointment at Bonn and Jülich, Stefan was scientific staff at Lawrence Livermore National Laboratory. Stefan is going to be talking about some work that his group has been doing that I think is very exciting on groundwater to atmosphere, so they include atmospheric processes and human water use at the continental scale. And now we're moving from Mark's great global overview now towards a more regional or continental approach, and Stefan is going to be talking about some work that they've been doing with the EU Cortex domain. As always, like last week, we're going to hold questions until the end of the presentation, and if you can type or chat your questions to me, and then I will ask the questions of Stefan towards the end. So let's all virtually clap again, and welcome Dr. Stefan Kollett, our speaker this week.
Yeah, thank you very much. I appreciate your kind words. And I would like to thank also CUAHSI for giving me the opportunity to present some of our work in this seminar series. I think the seminar series is really great. I think it's a great contribution to the hydrology community, and I feel we will be learning a lot also in the next few sessions. So okay, today I'm going to talk about groundwater to atmosphere simulations, including human water use at the continental scale, and as Reed already said, so it's kind of a smaller scale from last week, what Mark presented, but I think a lot of these topics that Mark presented are also relevant at this scale. So, of course, like always, this work is not done by myself. Of course, there are many people who contribute to this. And I would like to mention especially two people here. It's Mauro Sullis and especially Jessica Coyner. She really did all the work here on implementing the model at the continental scale, performing the simulations, and also doing the analysis. I would also like to very much thank our sponsors here from the Helmholtz Foundation that provided the funding, and also the Jülich Supercomputing Center and ECMWF in Reading in the UK, who provided us with a lot of the compute time. And also, of course, thanks to Yoshi Wada and Stefan Siebert, who provided the water use data I will be talking about too. Okay, so next slide here. So this is a cartoon of the terrestrial system, really from groundwater across the land surface into the atmosphere. This is a system we are trying to deal with. And this cartoon depicts, or tries to depict, actually some of the major processes really. So we have infiltration from the land surface, reaching at one point maybe the water table and becoming groundwater recharge. We have base flow towards the major river systems. We have groundwater surface water interaction here. We have, of course, processes related to the land surface, mass and energy balance, or water and energy balance related to evaporation into the atmosphere, and also plant processes like root water uptake and transpiration by various different plants. And then, of course, the major exchange with the lower atmosphere, which is mostly or entirely actually determined by the turbulence, by turbulent transfer of water, energy, and momentum. Then, of course, we have to deal with very complex, also microphysical processes related to precipitation generation. We have to deal with radiation, and so on. So this is a very simplified cartoon, of course, but I feel it gives some impression, at least, on the important fluxes. What's maybe not so well depicted in this cartoon is really the the tremendous heterogeneity of the system. So we really deal with heterogeneity, with variability of in parameters, in biogeochemical parameters, in physical parameters, from sub-centimeters to hundreds maybe or thousands of kilometers. And that the same is true for really the states like temperature, humidity, and also the fluxes that we just discussed. Another aspect that we try to depict here is, of course, the human impact. So we see here some agricultural fields, some agricultural heterogeneity introduced because of different crop types, and also some industry here. But of course, there's much more human impact that is really depicted in this little cartoon, and the water use impact, that is what I'm going to discuss today. What is the water use impact really from groundwater across the land surface into the atmosphere? So, okay, what's the motivation for us to look at human water use in addition to water resources management aspects? Well, I think it's pretty clear or intuitive, I would say, and we get to that. What's the impact on regional and global terrestrial water and energy cycles, and also biogeochemical cycles? I think it's also important here to remember that water use has not been implemented yet, in all, or I would say most, or maybe even all global or regional climate and land surface models. So really only a few land surface models, I would say, currently include human water use, and this might have impact also on the projections. Local effects on groundwater recharge and stream discharge and evapotranspiration. I feel these are impacts that are more intuitive to everybody. Like, of course, groundwater irrigation from groundwater abstraction will change ET, but what is also the impact on initiation of precipitation? I think these are the questions that may become important in future. And of course, then the non-local effect of groundwater abstraction irrigation. Well, what is the impact on continental discharge, atmospheric circulation, and then, as we mentioned before, precipitation and the evapotranspiration and the ET cycling rates. So these are really the questions that move us, and here I want to focus mainly on the non-local effect of groundwater abstraction and irrigation. Okay, so is it really significant? I mean, is human water use really significant? So what I was looking at recently is just, global water withdrawals from the information system for water and agriculture from FAO. And what you see here is just on the x-axis, you see the timeline from the 1900s to 2010. And here on the y-axis, you see the cubic kilometer withdrawals per year for different sectors like agriculture, industry, and municipalities and reservoirs. So from this information, we see that total we are around 4,000 to 4,500 cubic kilometers per year globally. So this is a global estimate. I believe this is a little bit on the lower end because, for example, what's not included here is really for example, the water quality aspect of withdrawals and human water use. Maybe on the higher end is really here some information on the water footprint. Also, this is a global map of the water footprint, including the three components of the virtual water, which would be green, blue, and gray water. And this is maybe on the higher end of human water use data, including also all the water transfers, actually. Okay, what we see here is, okay, let's say on average we have a water footprint of some 1,400 cubic meters per year per capita. Okay, and what I'm doing now is I take this number and I scale it up with the world population currently, which is about 7 billion, I believe. And so I can calculate, based on this, the mean global human water footprint of close to 10,000 cubic kilometers per year, which, if you look at some data on global water fluxes from Eschbach-Hertig and Gleason from 2012, which is about, it's on the order actually of the global groundwater flux of a little bit above 10,000 cubic kilometers per year, and it's about a quarter, of the surface water, global surface water flux of about 45,000 cubic kilometers per year. So in terms of just looking at the global picture, it appears, at least, it appears to be really significant. Of course, there's huge variability, you know, and we have to look really in different regions to really assess also the regional impact. But to me, it was also surprising that, well, I mean, it is really on the order of global natural fluxes. And this flux, of course, is increasing constantly, and it needs to be sustained. You know, that's also key here. So, so what factors are really important if we talk about also sustainability? And many people have looked into this, you know, into these things. What are the factors influencing sustainability? So we are not the first who also think about this. So there have been many groups, for example, that looked into irrigation cooling effect. And many people already also looked into local and non-local effects of irrigation on precipitation. For example, they looked at the processes. In this case, we're talking feedback processes. They interrogated if precipitation might increase due to irrigation, and they also showed that actually in regional studies. And then some other studies showed, well, there is actually no really significant response. So as I just want to point out here that we are, of course, not the first who really think about this. What we can really contribute to this, well, currently to this discussion, currently I would say if groundwater or irrigation water use is really implemented in land surface model and climate models, it's done in a rather simplified fashion. So for example, irrigation is approximated by keeping, for example, soil moisture at field capacity, or as is assumed that evaporation happens at the potential rate during growing season. So there's also now groundwater abstraction, of course, which would change the continental storage of fresh water and would also play an important role in sustainability. So that's where I feel or we feel we can really contribute something, and many other groups also go into this direction, like for example Reed's groups and also Dave Golch's group, that we want to include in these models really groundwater abstraction from shallow aquifers. We want to apply this more or less physically based at the land surface, and so we can really simulate then also groundwater and surface water depletion and also drainage and return flow, which plays, of course, a role in the transient of maybe, you know, storage changes in the aquifer and the soil zone. So this is really our contribution, I feel, that we can have also in terms of impact to the hydrology community. Okay, so what I want to do first here is really talk about a little bit about simple water budget considerations to address why we want to go from groundwater into the atmosphere, and also maybe highlight some feedback processes here. So this is a schematic now. So we go from this nice cartoon at the beginning, we move to a more schematic picture of the terrestrial system that we then later put into a mathematical model. But still we have, you know, still the same processes: precipitation, flux, evapotranspiration. We have groundwater recharge, base flow, continental runoff, and of course, very important, we also have, you know, the advection in the atmosphere. And we have, of course, then all the storage changes in the land surface, subsurface system, and also in the atmosphere. Okay, so now we can start with the basic moisture budget equations for the land surface subsurface system, which I write here as the storage change equals the precipitation, so the input to the land surface subsurface system, the output, let's call it the evapotranspiration back to the atmosphere, and here continental discharge. Note, what I assume here is that we deal with a closed continental basin, so our subsurface divergence of water is zero or close to zero. Let's say it's negligible in comparison to the other fluxes. Okay, that's the assumption I make, but I could actually include this in a very straightforward fashion. It's just, you know, it's a little bit simpler to keep the overview here, you know, to keep track of things, okay, just for presentation purposes. So we do this here for the land surface subsurface system, ups one direction, and we can do the same for the atmosphere now. We write here the storage change of water vapor the atmosphere, which is equal to the divergence. Now, this is important here for the atmosphere, because this is really a major flux. So the divergence, in essence, means it's really the difference between what comes in and what goes out in terms of water vapor. And this equals now the sink. You know, precipitation now becomes the sink for the atmosphere, and ET really becomes the source for the atmospheric water. What we can do is actually we can integrate this over not so long time scales, and we see that the change of vapor storage in the atmosphere over time is actually pretty small. So we can actually neglect that, because the atmosphere can store generally very little water because it's so dynamic. Okay, so we can reduce this equation, you know, to the form written here, where the divergence, you know, the difference between what's coming in and what's going out is equal to the sink, in this case precipitation, and ET. So this is really, I mean, note this, these two equations, they look really very benign, right? I mean, but there's a lot of physics behind these two simple equations. I mean, we're talking here on the divergence, we're talking here about coupled momentum, energy, and water balance equations for the atmosphere, including also movement equations. Here, for example, precipitation. We are talking microphysical processes that have to be represented in atmospheric models. And the same is true really for the land surface subsurface system. You know, I mean, change in storage here means, you know, all these processes that I just mentioned, like groundwater recharge and base flow and discharge, and also simulating continental runoff and exchange with subsurface storage it's really a major feat. So don't be tricked by these simple equations, but I mean, they at least they can give us some insight, because what we see immediately here is that we can actually merge these two water budgets from the atmosphere and the land surface subsurface, and then we arrive at actually one simple budget equation for this full system, where we can include the atmospheric transport in the land surface subsurface balance equation. And we see really that, well, I mean, atmospheric transport really feeds back with the storage of the system, of the land surface subsurface system, and continental runoff, and vice versa. I feel this is very nice, so we can, you know, really see why we actually should really go from deep groundwater into the atmosphere, also based on these very simple balance equations. Okay, what we have here now, it's kind of the pristine system, right? I mean, there's no groundwater well in here, and there's no irrigation. So that's what we're going to do in the next step. So we want to include, for example, groundwater abstraction and direct irrigation here. And I would say that we all agree that, you know, if we do this, we, let's say, increase ET. Okay, maybe we can agree on this. But what happens to the other fluxes? I mean, these are just big question marks. So what happens really to precipitation at the local scale, and also then on the regional scale? What happens to the divergence? Meaning, you know, do we increase transport of water vapor, or do we decrease it? The same is true for continental runoff. Do we decrease or increase it? So there are many question marks on this figure, which we then try to address with our simulation. So now let's go to the balance equations again. What we do now, we introduce here groundwater abstraction and irrigation, and you know, I indicate the storage change here with human water use. In this case, it's different, and it looks from this equation, if I do this and I assume here now abstraction is equal to irrigation, it almost appears like, well, I could do this forever, right? I could just circulate this, you know, and I could, you know, basically do this without any impact on the land surface subsurface water cycle, which is of course not true. I mean, because, well, I mean, we introduce change. I mean, these two terms, which are very small, in fact, actually, when you look at the continental scale, they really induce and amplify a change in evapotranspiration, and they do maybe the same for precipitation and also for continental runoff. Okay, so that's, you know, through the process, let's call it the process, through the process, for example, how plants work and how evaporation works, ET is changed by these two fluxes. I want to say one thing, this equation is wrong. Why? Because I write these changes in ET as and P and precipitation and runoff as linear corrections. This is of course not true. You know, these are highly nonlinear systems, and the correction or the change in ET is not simply a linear correction, but I put it here just to illustrate what's happening. Okay, now I can do this the same thing for the atmosphere, and I put in here again these nonlinear corrections because precipitation might change and ET might change. Again, you know, these are just for illustration here, these linear corrections. But what I see immediately that indirectly through abstraction and irrigation, we're gonna change the atmospheric transport. Okay, we're gonna do that, you know, and that's why our rationale is we have to go from groundwater into the atmosphere. And okay, we can again insert this the atmospheric transport in our land surface subsurface balance equation, and we see, well, you know, pumping will influence atmospheric transport, and in turn maybe will influence storage changes and also continental runoff. Okay, so this is something we are interested in. Okay, so what we do is we expand these very simple equations and develop a mathematical model from groundwater into the atmosphere, what you see are the equations for the subsurface. So it's basically the mass balance equation, and with a movement equation, Darcy equation, it's basically Richard's equation in 3D. So we solve the system as a continuum in 3D from groundwater to the land surface. We couple, or we integrate, we do not couple, we integrate overland flow. Then we use similarity theory to really approximate turbulent transport, here expressed in terms of evaporation flux, and couple then to the atmospheric equations, which are in essence the compressible Euler equations, which are not written here in the complete form. Okay, so what I'm going to do now in the next, would say half an hour, what is left, I probably just go through these equations and discuss everything in really detail. Now, I'm just kidding. I will not do that, of course. Okay, I will talk about this. I will talk how groundwater abstraction irrigation, which appears here as a sink source term in our Richards equation, will feed back into the atmospheric system. Okay, no worries. Okay, so these equations are implemented in our coupled modeling system. It's our terrestrial systems modeling platform, TERSUS MP, where we treat the atmosphere via component model, which is COSMO. That's the weather prediction system of the German Weather Service. We have CLM here, the community land model, to handle the land surface, water, energy, and also momentum balance. And then we have power flow for the subsurface. So for the continuum simulation from groundwater to the atmosphere, and also including surface water or overland flow. So, I mean, yeah, for example, Reed's group is doing the same with Pavlo Wharf. Dave Goges is doing similar things with Wharf Hydro. So again, we are not the only group here that is trying to go along these directions. But I just want to introduce our approach here. Okay, so we couple these component models via an external coupler. It's OASIS MCT. Which is a sophisticated coupler that comes from France, from Surfax, and really Prabhakar Shrestha at the Meteorological Institute in Bonn did most of the work of this coupling also, and Fabian Gaspar here, he expanded this to OASIS MCT, and we did a lot of optimization, tuning to make this modeling system work on these massively parallel computer resources we have in Jülich, and how they exist also in the US and many different places. What's worth mentioning is that this system is also implemented with a parallel data assimilation framework from the Alfred Wegener Institute, and Wolfgang Kurz and Harian Hendricks Fansen from our institute. They really did a very nice job in integrating TERSUS MP with PDAF, which is based on the ensemble Kalman filter approach, and now we really have a nice system set up to also merge our our models with observations, but I will not talk about this here. Okay. Okay, so it's a highly modular setup, so we can easily drop in and out different component models. For example, we can remove the subsurface path flow and perform a more classic atmospheric simulation with the land surface model as a lower boundary condition, or we can take out the atmospheric model and perform more like a classic offline hydrologic simulation. So it's kind of a neat setup that Prabhakar et al. Developed here. And of course, what I'm going to talk about is a fully coupled system from groundwater into the atmosphere. I just want to mention this week, actually, now we have a fall school where we talk about these modeling concepts and also talk about more HPC and the geosciences. So maybe next year, this would be a nice way to get familiar with these systems for you. Also, this is available online, so in a Git repository where we also provide, for example, input data sets and validation data sets where you can run this system on also like a PC over a regional scale watershed. Okay, just to mention that. Okay, so now Jessica did the implementation over Euro Cortex. What she did is she implemented the model at this point at 12-kilometer resolution, including Cosmo, CLM, and Parflow. Cosmo runs here at 60-second time step. We run the land surface model and the subsurface model at 3 minutes, so it's really at a very high time step because we want to capture most of the nonlinear feedbacks. So she drives the model with error interim data along the boundaries here, and she performs a spectral nudging at the top of the atmosphere to keep, let's say, the big weather systems close to reality. We're doing this to maybe in future also to compare more comprehensively to observation. So there's a lot of input data that she has handled, for example, related to plants, related to the soil, related also to the hydrogeology. And I will not go into this in detail because there's a very nice publication by Jessica where you can find all the information on how this model was informed with input data. So what Jessica did is she simulated 1 year at this point of the year 2003 of the European heat wave, because we expected, of course, a lot of strong feedbacks during this time in Europe. And she performed five simulations. So she did one reference simulation without water use to compare to with in total 4 water use simulations. So she used 2 different water use data sets from Yoshi Wada and Stefan Siebert, and with an explicit groundwater pumping from shallow aquifers and irrigation at the land surface in our coupled modeling system. And she applied 2 different irrigation schedules, very arbitrary. She did one during the day and one during night. Okay, and what she in essence did is really it's a sensitivity study of human water use, utilizing a small ensemble, including 4 members. That's how we see it here. What we present. Okay, what I want to say is this model is, of course, work in progress. Okay, it's a model at 12 kilometer with the freely available input data, and we constantly try to improve the model. For example, now Wendy Sharples in our group, she's now going from 12 kilometer to 3 kilometer resolution, and she is working a lot on improving also the geology of the system. So that what you see here, this is a hydrogeologic map from the Federal Bureau of Georesources in Germany, where they developed with colleagues in Europe like a kind of detailed geologic map, hydrogeologic map of Europe that we are now trying to implement consistently also in our model. So there's always ongoing improvement. So these model developments never stop. Okay, that's really the essence. And I think we will go also like also other groups like Reed's group, you know, in 5 years I feel many groups will have very detailed hydrogeologic models representing a lot of the heterogeneity at the continental scale. Okay, here you see what's very nice now. You can see really at this, with these maps already, these alluvial valleys, alluvial aquifer systems in the valleys surrounded by the bedrock, and this is really important to accurately simulate continental drainage. Okay. So what happens now if you use this type of terrestrial systems models, which are more physics-based? So what you do is you initialize these models with a very arbitrary hydrodynamic initialization, and then you run these models over very long time periods that we call spin-up into some hydrodynamic equilibrium that is consistent with the atmospheric forcing, with the atmosphere. And this takes a while, but it's very neat to see. The river systems come up, the continental drainage along these major continental river systems is established, and all of this because of this continuous, let's say, treatment of the hydrologic system from groundwater across the land surface. So yeah, and this shows you a picture of let's say dryness and wetness. So you see here the major river systems like the Danube, which is of course very wet, and then you see here, for example, the Rhine River system, and you see these very dry patches in southern Europe, in Spain and Portugal, which at least shows some that the model is developing realistically. Okay, and then the output ultimately, then, for example, what you get out of these simulation is, for example, water table maps, not only maps, but we simulate this in a dynamic fashion, and so we can interrogate the system really at different points and, for example, extract water table depth information, which we then also can compare very nicely with observations. And you see really here that we can already get at 12 kilometers, we get already some really nice details of the system. Okay, so in this system now we implemented the water use data sets, including groundwater abstraction and irrigation. What I do here is also in the next slides, the results are, let's say, semi-quantitative. Why? Because we are still in the process of publishing this information. I apologize for this, but I think this is an appropriate way to present this data at this point. Okay, so like you see here at the top, this is data on the groundwater abstraction from Stefan and from Jülich here, and you see that there are some differences, over the year and also in total groundwater abstraction. But this is exactly what we want. So we want really these differences in different water use data sets to address also uncertainty in this information and to see if we actually get a systematic response due to groundwater abstraction later in the models. And here you see similar things for irrigation demand. You see again that Stefan has slightly higher values than Jülich, but again, that's really what we want to have. We want to have these difference in the input data sets. Okay, so spatially also, it's very nice to see that these data sets agree very well. And this is the case also for groundwater abstraction here in the top panel and total irrigation of 2003. And I feel that this really lends some nice confidence in these data sets, so that they have some consistency spatially. This is very important for us in this case too. Okay, now what we quickly look at changes in maximum daily temperatures, and we do this here for two major regions. We do this for the Mediterranean area and the Iberian Peninsula, and what you see here is the descriptive statistics for the spring, the summer, and also the fall. Here on the y-axis, you see the difference of the water use simulation from the reference run in terms of temperature and Celsius. And we see, well, that, for example, here irrigation during the summer months causes quite some cooling, of up to 0.5 degrees Celsius in the Mediterranean region, and very similar magnitudes also in the region of Spain and Portugal. This is actually not something new. I mean, this is almost it's a corporation of previous findings that have been discussed also in literature. If you look at the spatially distributed, there are also no big surprises. Actually, what we see really is that where you have heavy irrigation, that you see the major cooling, actually the major cooling effect. What you see here, these are the results from the 4 water use simulations. So and for the year, not for the year, for the season of summer, so June, July, August. And I mean, these patterns are expected and really corroborate also what previous studies found. What I find is interesting is the change in convectively available potential energy. Probably many of you are not available with this variable. It is really a variable for the atmosphere, and it is an indicator of atmospheric stability. So very high CAPE values would suggest that probably there might be more frequent or let's say severe weather initiated. Okay. What we do here, we actually integrate this variable again over 2 different regions, over the Mediterranean area and the Iberian Peninsula. And here you again on the y-axis you see the difference in CAPE between the water use simulation and also the reference one. And you see a tremendous response here during June, July, and August, where we see on average larger CAPE for both water use simulations. And you see a much larger variability also to higher values, which suggests that the atmosphere actually becomes less stable, leading also to changes in precipitation patterns. I think this is also a nice way to demonstrate the feedback between human water use and atmospheric processes and atmospheric transport. Okay. So now if you look at total precipitation, if you look at precipitation, what we did here is we integrated this over the full year over Europe, and we see that the reference run has about 887 millimeters precipitation, and we see that with water use simulations we arrive at slightly smaller precipitation estimates, average or mean annual precipitation estimates over Europe, which are 1 to 2 millimeters smaller. It's kind of interesting to compare this value, for example, to previous estimates of the impact of groundwater abstraction to sea level rise. And for example, Konnikov did this analysis, and also Yoshi published on this recently. And actually, you know, these values are in their estimates are actually not so small. You know, I mean, of course, you know, considering all the uncertainty we have in these simulations, 1 to 2 millimeter appear very small. But if you talk about the global aspect, and for example, also the contribution of human water use to sea level rise, actually 1 to 2 millimeters is significant, because that's actually the water that might end up in the oceans. And if you look now regionally, if you look over the France and the Iberian Peninsula, again, we see, well, in some regions, the difference is more significant, is much larger, and goes into the tens of millimeters. And that is, of course, you know, of great concern would be of great concern to water resources if these kind of differences persist throughout multiple years. Okay, so how does it look spatially? And this is really interesting, is that we look at the difference in precipitation, we look at the spatial pattern of the difference in precipitation over Europe. Again, for the 4 different water use simulations, we see that these patterns are very consistent. So we see really that in some regions in spring, now we are talking spring here, that we have a consistent increase in precipitation, also regions where we have a consistent decrease in precipitation. And the same is true here for evapotranspiration, which I feel is a little bit less surprising, because of course ET is a much more local process in comparison to precipitation, which depends a lot on atmospheric transport and is characterized by a lot of chaotic processes. And going now to the summer months, we plot again the same water use simulations here on top for the difference in ET, and here at the bottom for the difference in precipitation. We see again how these differences in precipitation persists throughout the different water use simulations. So, and this suggests really that human water use in terms of groundwater abstraction and irrigation induces spatially systematic differences in atmospheric transport, which we feel are important to interrogate further. Here again, in terms of ET, the picture is even clearer. We interpret this because ET is again a much more local process than precipitation. Okay, this of course feeds back into storage changes and also into continental runoff changes. What I show here is the change in continental storage. This is the full water column from the bottom of the aquifer to the land surface, and we see that these differences in P minus ET that we saw previously, they propagate into storage changes locally that are then of course also consistent between the different water use simulations, and also they will also impact the continental runoff along these major river systems, which of course is part or must be included in these sustainability considerations. So I hope I can demonstrate here really that feedbacks with the atmosphere, the change in the atmospheric transport plays a major role, and that non-local effects via the atmospheric transport have to be considered if we talk about water use at the continental scale. So we feel to study these processes, the groundwater-to-atmosphere models are useful tools, and also to assess the impact on the terrestrial water and energy cycle. The water use has local and non-local impacts. Some of them are very intuitive. For example, the potential cooling effect in the summer. But it's also very interesting to see that we arrive at systematic, spatially distributed changes in evapotranspiration and especially in precipitation, which we attribute clearly to atmospheric non-local transport processes. And during summer, the systematic impact on atmospheric moisture transport apparently redistributes water resources across the continent. So now the question is for us really, do atmospheric feedbacks need to be included in sustainability considerations related to human water use? Well, I mean, to answer this question, I think it's a very concrete question. What we need to do is we need to perform longer-term simulations, including human water use at higher spatial resolution, really at resolutions that are more relevant for hydrology also. And then, of course, what we need is we need to additional water use data sets, and we have to use more efficient or more realistic irrigation schedules to also capture all the uncertainty we have. We have to also include, of course, engineering structures in these models, and we need to fuse our models with observation. It doesn't matter which ones. I feel we should use all of them basically, in situ and remote sensing, because it's amazing that we just even the current state of the system, of the continental water system, is largely unknown to us. So we just simply have no idea what the state of storage, for example, of groundwater storage is at a given point. So if for example, a farmer comes to us and asks us these questions, we can simply not answer this. So we don't have an idea of the system at the continental scale. We only know it maybe at points. So we have to do something about it, and I feel this is really our vision. What we want to do is, what we strive for is, we want to fuse our models with observations. Here depicted as little satellite remote sensing information, and we want to do this really from the local scale across the regional scale to the continental scale. And we want to do this via efficient parallel data assimilation technologies And this way, we want to come up with a scale-consistent, integrated terrestrial modeling and data assimilation system from the subsurface into the atmosphere, where we can really generate best estimates of the current water state of the system and also energy state of the system, including uncertainty bands, and that we can then use really to initiate, short-term forecasts, seasonal forecasts, and also long-term projections. Okay, so this is my 50 cents, and I'm really happy to answer any questions if there are any. Okay, thanks.
Okay, thank you very much, Stefan. That was a great presentation. And we have plenty of time for questions and discussion. So remember, please type your questions to me. I'm going to sort of sift through them and organize them a little bit and then ask them to Stefan. So, first question. The first question wants to know more information, perhaps about how you incorporate water table increases or decreases due to irrigation. And so maybe you could just expand on that connection and model a little bit more.
Yes. So what we do is our subsurface model, which is in this case PARFlow, is a continuum model. So we solve Richard's equation, and this equation holds in the saturated zone and also in the Vado zone up to the land surface. And so water table dynamics are included in the equation. That's really the case. That's why we call it the continuum approach. And the wells, the abstraction is implemented as sink terms in our Richards equation and react fully dynamically to the abstraction of groundwater, and also, that's important to remember, also to return flow from irrigation, which would in some areas increase groundwater recharge. So this is handled in a fully dynamic fashion. Of course, we do this now at the 12-kilometer scale, so we cannot reproduce very local cones of depressions around irrigation wells. That's what we cannot do, at that resolution. So we get an average water table dynamics or average water table decline, or maybe increase because of increased aquifer return flow at the 12 by 12 kilometer scale.
Thanks for that answer. So to follow up a little bit, so then you pump at a given depth, so you assume that all the farmers are pumping locally at some given depth, and then is the irrigation applied as spray or drip? Is it above the canopy or below the canopy?
It's applied directly at the land surface, so it's below the canopy.
Gotcha.
And that's a good point. That would be very interesting, actually, to change that. That's a good idea. Yes, very interesting. Huh?
I still have them occasionally. Okay, so the next question is, GRACE is one way to monitor, or was, unfortunately, one way to monitor continental water storage. Are there any other remote sensing tools that are coming up that would augment this? So maybe if you could expand on your thoughts on how remote sensing can be integrated in these types of modeling frameworks.
Yes. So I feel, currently, of course, the follow-up mission from GRACE is coming up, where we would expect a lot of useful information, especially to constrain our storage estimates or storage change estimates. And at that scale, actually, these kinds of observations make a lot of sense. And also, SMAP, for example, would be very interesting to incorporate. And we are already try to get our data assimilation at the continental scale running, but just using CLM currently. But yes, this would be some interesting input data sets that could be used, in my opinion. And of course, altimetry data for surface waters would be also another option. So
a very highly related question. In terms of the challenges, in terms of model data fusion, do you think that temporal or spatial is more important? So the question asks, would you increase the time step or or run duration or increase in spatial resolution? Which do you think is more important?
Yeah, so I think, I mean, in this case, as I mentioned, we already run at a very high time step in terms of hydrology. So we run at 3 minutes, we couple at 3 minutes. So I think this is almost like overdoing it, but we wanted to make sure that we really capture all the nonlinearities. A spatial scale, of course, spatial resolution. This is really, I think, this is for us the next important thing to go to higher spatial resolution. It's almost like an atmospheric model. Now in atmospheric simulations, now people move to the convection resolving scale. So they simulate now continentally, or even at the globe now, they go towards kilometer scale resolution to resolve deep convection, for example. And in hydrology, it's very similar. We can resolve processes much better at higher resolution.
Great. So then a follow-up question here, which comes from Ted Endre, is how are urban issues or urban interests resolved in your model? And this question points out, obviously, that human population is concentrating in urban areas. Yeah. Urban water systems have their own challenges, and how might these be incorporated or affect your model simulations?
Yes. So yeah, that's a very good question too. So I would say the urban areas are the poor cousins in our model. I mean, we have no detailed urban model in there. No, not at all. I mean, there are very detailed urban models, like urban canopy models, also for the exchange with the atmosphere, and we have not yet put effort into improving our representation of urban areas in this particular model. But this is something also that really needs to be worked on. And yeah, that's a good point. Thanks.
So a question from Steve Burgess. Steve has also contributed some great questions last week as well. And Steve wants to know how you might use GRACE data, or if you can use GRACE data to basically check the water storages or the change in water storage in your models, and at what scales might you do this?
Yes. So yeah. So this is a very important point to compare to GRACE. We have a group here also at the University of Bonn, Jürgen Kusche and Anne Springer, the student, and they work on this. And well, I mean, at the continental scale, it starts making sense. Or let's say continental watersheds, it starts making sense to compare to GRACE. And for us, you know, it's very interesting even to just juxtapose the storage changes that we get out of our model and that GRACE observes. We're not even talking about data assimilation at this point. For us, it's really just very instructive to just juxtapose the evolution of storage changes from this observation and with our model. I'm not sure if this answers the question, though.
And I guess a maybe more naive question. How many GRACE pixels, if you will, do you get over the Cortex domain?
Oh, so we have Europe has Europe has an area of some 10 million square kilometers, and I didn't do the calculation in terms of GRACE pixels, but GRACE is on the order of hundred by hundreds of kilometers. So I did not do the calculation how many square pixels we get out of this. So yeah.
But there are enough at this scale that you can start to resolve some differences.
Yes, absolutely, yes.
Great. So then a more big picture question is you are increasing your model complexity. You're adding in groundwater, for example, into this continuum system. And other approaches have done these sorts of irrigation experiments without groundwater. Where do you see the complexity paying off, ending up? Can you speak more to the spectrum of complex to simple models to answer these kinds of questions?
Yes. So yes, I mean, I feel these studies that have been performed and that approximate water use via irrigation, also excluding groundwater abstraction, I feel they're very interesting, and we learned a lot from them, and these results stand, in my opinion. Okay, I feel really the contribution of our groundwater or let's say groundwater model, including the full feedbacks, is that we can perhaps better identify the pathways of impacts later. So, for example, if really atmospheric transport changes, you know, what kind of pathway will it have later? Will it change groundwater divergence? Will it change, you know, continental discharge because we change base flow? We actually simulate or attribute also groundwater pumping to reduction, for example, or increase in continental runoff, because we can include stream depletion by pumping. Okay, I think this is the added value of the complexity.
Terrific. Well, I think I'm going to pause things there. A lot of great questions. That was a really nice presentation. And as we did last week, we're all going to virtually clap. Even though it's just me clap alone in my office, to thank Stefan for this really nice presentation. But you know, we have to thank the speaker, and it's awkward to thank the speaker over a cyber seminar. So just to note, there will be this entire cyber seminar series is going to be recorded or has been recorded and will be available for offline viewing for those who didn't get to catch it or want to go back and study some of Stefan's sanitized figure graphs a little bit more. And next week we have Dave Gotchis from the National Center for Atmospheric Research talking about the U.S. National Water Model, so we're jumping continents. And thanks again for your attendance, and we will see you all next week.
Okay, thank you.